Good morning, good afternoon, good evening, good night, good whatever time it is where you are. Welcome to today's Math Minute. I wanted to record a follow-up to the Math Minute that I did last week on Simpson's paradox. So again, Simpson's paradox is this weird statistical phenomenon that happens sometimes when if you look at an overall data set, it might tell a certain story in terms of relationships, correlations, positive correlation, negative correlation, that when you chunk up the data into smaller data sets by some factor, it does not tell the same story. In fact, it might tell the exact opposite story. You might remember this is what happened with some vaccine data that came out of Israel in August 2021, right, last month, where we saw, and I'm going to go ahead and calculate this in just a couple minutes, we saw that there was some data on vaccine efficacy, and it showed 92% effectiveness for an under 50 population, 85% effectiveness, still really good for an over 50 population. It wasn't super clear from the original data, but that was including the 50-year-olds in that over 50 population. So it showed these two relationships, 92% and 85%, and yet the overall effectiveness was only 67.5%. Now, I can't remember if I said this in the other video because I also posted a version of this to, that other video platform. 67.5% still good. So even if in some sense it were true that the vaccine were only protecting you 67.5%, making you basically a third as likely to get sick as someone who was unvaccinated, that would still be really good. That notwithstanding, I wanted to run through the calculations, and we only need 8 numbers to generate all the other numbers in that table that I looked at last time. Some people said that table was a little confusing, so that's why I wanted to go through this. With these 8 numbers, we've got the actual cases among our vaccinated, unvaccinated population, under 50, over 50. And then, of course, we have the sizes of those groups, which are very different. You can see we've got a group as small as just a couple 100,000 people. That's the over 50 unvaccinated group. And then our largest individual group is the 3.5 million people who are under 50 and vaccinated, though by percentage, it's definitely this over 50 vaccinated group. That was 90% of that population. So the first thing we want to do is normalize this by rate. And again, I'm going to go through these calculations one at a time, and then I'm going to use the magic of Excel to have it do the rest of the calculations for us. To normalize this rate, we just want to take a look at the number of cases from that, in this case, under 50 unvaccinated population, and then divide by the size of the total population. And then just to make the numbers nice, we're going to do this per 100,000 people. So we're going to multiply that by 100,000. So let's do that now. We're going to take those 43 cases, divide by the total population under 50 unvaccinated, and again, we're then going to multiply by 100,000, and there it is. That's the 3.85 cases per 100,000 people if you are unvaccinated and under 50. Now, like I said, we're going to use the magic of Excel to carry that formula over, and so now you can see all 4 of those case rates for these individual populations. 3.85 cases per 100,000 people if you are unvaccinated, under 50. 0.31 cases if you're fully vaccinated, under 50. 91.9 cases per 100,000 people if you are unvaccinated, over 50. And finally, 13.59 cases per 100,000 people if you are fully vaccinated and over 50. Now with these numbers, we can go ahead and calculate vaccine efficacy. Vaccine efficacy, according to the CDC and I guess other World Health bodies, turns out to just be a percent change. It's essentially the percent change from our unvaccinated rate to the fully vaccinated rate. And so that's what I'm going to calculate right here. That's going to be 1 minus that fully vaccinated case rate per 100,000 people divided by that case rate per 100,000 people for the unvaccinated population. And you can see that's where we're getting our 92% effectiveness. This one's not hard. I'm just going to copy the formula down. I won't even use my magic snap. And there we go. 0.85, 85%. Is that vaccine efficacy for your over 50 group. Again, comparing these two numbers. Now, up to this point, you might think, well, all well and good, but how are we combining these two numbers and generating that 67.5% overall efficacy for the total population? And if we were combining these numbers through some kind of weighted average, depending on these populations, it would not work, right? It would not give us some number outside of 85% to 92%. It would have to be some number in between based on the sizes of the groups. But to compute the total population vaccine efficacy, we don't just combine these two numbers now. We're actually going to rerun our calculations for the total population. We're going to look at all 301 cases among the fully vaccinated total population, the 5.6 million people that we're looking at there. We're going to look again at all 204 cases or 214 cases that it works out to. So I need some new information in my Excel table to jot this down. And you can see that's what I've got down here. I have added together all 301 cases. That is up here, the 11 plus 290. I've added together all 214 cases among the unvaccinated populations. And I've taken my sums, total unvaxxed population, about 1.3 million, total vaccinated population, about 5.6. Now again, these are obviously very differently sized groups, and so we want to normalize by population. We're once again going to calculate cases per 100,000 people. So there it is. I've got some new rows and columns here where I can chart this information. Fully vaccinated cases per 100,000. Let's take those 301 cases, divide by the fully vaccinated population, and again, just to keep the numbers nice, multiply by 100,000. That's your 5.34 cases per 100,000 people among the fully vaccinated population. Copy that over. Excel is amazing. 16.42 cases, same calculation, 214 divided by 1.3 million times 100,000 people. And finally, our total population vaccine efficacy is just that percent change. The fully vaccinated population's case rate per 100,000 divided by the unvaccinated population's case rate per 100,000 subtracted from 100%. 67.5%. Seems wild, seems like it shouldn't be possible, but in fact this is what happens. Now one thing that's nice about having this all in an Excel table is we can now change some of these numbers around and start to see how they're affecting this overall total population efficacy. Specifically, I'm going to adjust the numbers in this over 50 population. I'm going to keep their ratio the same. So you're going to see as I change the numbers, that vaccine efficacy among that group stays at 85%. But the sizes of the numbers I'm going to make difference. For example, I could make them larger by a factor of 10. And you can see within that population, obviously, your vaccine efficacy is still the same, because again, the proportion of cases has not changed. But obviously we have way more cases just in terms of the absolute numbers, and that definitely changes these populations of cases among your total population. And that brings vaccine efficacy way down in that same total population. In the same way, we could cut these cases by a factor of 10. We could change them to 17 and 29, keep that efficacy in that over 50 group at 85%, because again, the proportion of cases is the same. But now that we have lowered the total cases so much, we see vaccine efficacy in the total population go way up, go up to that 85% number. If we essentially divide by a factor of 10 one more time, you can see now our vaccine efficacy among that group actually goes down to 74%, even as total population efficacy gets way closer. In fact, it exceeds a little bit our 92% of efficacy among that under 50 population. So it's all about how large those absolute numbers are. When we keep them where they are, we can see that Simpson's paradox happening. The overall population numbers look way different than anything we would expect based on the subpopulation numbers. It's not a weighted average, it's a new calculation entirely, and that's how you come up with it. Super interesting numbers, really weird how they're interacting together. Great real-world example of Simpson's paradox. Use it as you see fit. I hope that was helpful. If there is other stuff you're interested in that you would like to see me do a video on, comment down below. Like and subscribe if you want to see more videos like this, and otherwise I will see y'all next time.